Hello everyone, welcome to Kaggle Basics video 4. We're going to dive deep into some data science for this video. We will go directly to the heart of Kaggle and learn how to apply new linear models as well as submit solutions to Kaggle competitions. So we're going to dive into the matrix to do that. Let's go to right here, Kaggle.com, and get started. So, what we can do is click on code. We can go to our last code real quick, which is under your work. Click this one and hit edit. And now we will run this code here. Turn it on. And I'm just going to click run all as soon as I can. I'll turn on the GPU accelerator as well. I guess we now also have access to TPU v38. I'm not sure if that's faster or not. I haven't used that yet. So I'll hit run all. This should take a few minutes to run. So let's scroll down. We've already gone through all this code in the previous video, where we are cleaning the data, we are dropping the data, we are looking at the distribution of different variables in our data set. We looked at the QQ plot, and here's the missing data, so we go through all of that. Keep going. We drop all of the missing data or substitute some missing data with the most common data. Keep going. Switch back into a training and test set on this line of code. And now we get to the Sklearn linear models. If you remember, we used a combination of models. So I started looking at different linear models, and I'll show you how to implement some new ones. Let's say we don't know how to use all of these. This was our cross-validation score, RMSLE, and we had all of these different models that we used: ElasticNet, Lasso, Bayesian Ridge, Lasso Large IC, SGG. I'm not sure which ones he had in here before, but I added SGD Regressor, I believe. So he starts with Lasso, then SGD. This is the one I added, SGD. Stochastic Gradient Descent. SGD. And how did I do that? Without really, I know what stochastic gradient descent is, but say you don't know what it is. I don't know what ENet is, or I think I know what kernel ridge is. But these are all the definitions of the model here. We're defining Lasso, SGD, ENet, KRR, gradient boosting regressor. We have all of these variables here. What do they mean? And then we test them here. So it's actually not taking so long. This code will actually run pretty quickly, so I may be able to show you some things. These are all Sklearn linear models. So I will attach this in the description for the video here. Here are the Sklearn linear models. We can go through them all. There's ordinary least squares. There's ridge regression and classification. They all have some sort of mathematical formula to them in order to fit the data. They all have strengths and weaknesses. Here's Lasso. The Lasso is a linear model that estimates sparse coefficients. It is useful in some contexts due to its tendency to prefer solutions with fewer non-zero coefficients, effectively reducing the number of features upon which the given solution is dependent. For this reason, Lasso and its variants are fundamental to the field of compressed sensing. So there's the formula. They have examples here. If we go to examples, let's see if we can find an example of actual code somewhere. Here's LARS, least angle regression. So here we are importing a linear model. We're using Bayesian ridge. And how do they define Bayesian ridge? Or they just use it. They don't have to define any of the variables for that. But if you were using Bayesian ridge, you click the link here, you could see all the parameters that you can define. Do they ever show an example of them defining parameters? No. But you can define those parameters. For the one I did, let's go to that. Let's go to stochastic gradient descent, SGD. Let's hit this one here. Import SGD. Here it is. Here's the model. Except this is classifier. Oh, darn. Regressor. We're doing regression. We're not classifying. We're doing regression. So two different types of machine learning there. If we go down, you can see all of the variables defined here. So if I go back to my code, when I define stochastic gradient descent, I do make pipeline, standard scalar, SGD regressor. The loss, I do the Huber function, iterations. I define all of these variables that are required in order to utilize SGD regressor. Here's the definitions for all of those, so you can learn what they are and determine which ones are the most important for the accuracy of your algorithm, of your machine learning method. So here's a definition of all of those. Here's the code that turns it in. So you can literally just kind of copy and paste this. But here's the part where he makes the model. reg equals make pipeline, standard scalar, SGD regressor, max iterations equals 1,000, and TOL equals that. So I can literally just copy and paste this, use it on my data set, and see how well it predicts. So that's what I did. Let me teach you a hotkey real quick. Let's do it for, this one takes a while, but let's say you want to improve any of these, any of them. Not kernel ridge. Let's do gradient boosting regressor. Click the box here, push B, and now let's go to the line of code that measures how well the gradient regressor does, which I think is this gboost. Control C. And you could loop this to do it an even better way. He initially had a learning rate. A learning rate's a good parameter to adjust because you want to optimize your learning rate to get the highest accuracy. So let's put in 0.05. Shift enter. That's taking longer than it should. Oh, the code's still running. Oh, darn. I should have ran this beforehand before I started this video. Well, I can talk about something else then. What I'll talk about in the meantime while this code is running here, because I want to show the accuracies of all of it, I'll show you how to submit on Kaggle competition. So let's go to Kaggle and go to competitions. So let's look at my submissions. I submitted one, and currently I got a public score of 0.119792. If we go to the leaderboard, we can jump to my leaderboard position. Here you got 1, 2, 3, 4. Click it. I'm at 147 on the leaderboard. So that's pretty high. You don't get any points or anything for this, since it's not a competition anymore at this point. It's not an active competition. It's more of a learning competition. But this is a good score to get. And I got it just from using that code that we just found together and making slight adjustments to it and improving it. So how did I submit this? You just go to your code. Go to code. And I think this is already being run in a different window. So let's not go to that specific code. Any code will work. You go here and you click submit. And what will happen when you click submit is it'll run this entire line of code for you. And you need to produce something called submission.csv, an Excel file. That's your submission file. So it'll take your code and run it on its own when you click submit. So you don't need to like run your code first or anything like that. It's actually very easy. If I click submit, it would run this code right now. This one wouldn't work because it's not it doesn't create a submission file. But the one that we were just looking at does. Okay, good. Good. And this is the submission file at the very end. So if I click submit, it'll do it. It'll take, however long it just took to run this code, which I think was about 10 minutes. And it will get you a score like that just by running this code. Now, how did I improve on the score here? We used an average-based models approach here and stacked the models as well. So I just added another model to it, and it improved it slightly. So let's go back up. And I also optimized some of these parameters here. So when I run this, what kind of score do we get? Learning rate of 0.05. So we have 2 lines of code here. Let's hit stop, just so I can show this better. Let's put that on 1,000. Kernel Ridge. Okay, so we did get one score here. 0.1166. So in order to test that or improve that, let me lower the learning rate to 0.4, or I'll lower it to 0.2. So we got 0.166. Does this improve our score? And you could loop this and plot a bunch of different learning rates and a bunch of the results and figure out where the optimal rate is. And you do that with each of these different linear models that we're using, because they have all of these 0.155. So we did better with that. And if we increase the number of estimators, it would take longer to compute, but that would also improve it a little bit. Kernel Ridge, we could do the same thing. You click here, you push B, you paste it, you run that, and 0.153. That one does pretty well. I don't know what the alpha does there, but let's just change the degree to 3. I think that might end up making it take a long time. Oh, it did better, didn't it? 0.13? No, it didn't do better. Yeah, a lower score is better. So 0.11 does better. What if we raise it to 4? Fourth degree polynomial. It's not doing any better. So we'll keep that at 2. And this is part of what doing the data science is. If we go back to this page here, we can click back. And we were just looking at kernel ridge regression. And you can find out what those parameters are, learn what the parameters are, and start adjusting them. And that's how you improve your model, by adjusting those parameters. These few numbers here, you learn what they are, you learn what alpha is, and you adjust it to improve. 0.156, so we're pretty close there. 0.153. 0.1151, so we did better there. If you run it more than once, you sometimes could get, it could be some random thing where you get different results there. What if we go to 0.8? It goes down again. So these are the values that we need to optimize to improve our accuracy. Now we continue to go down here, and so initially the code did not have gradient boost and regression. I added that. No, not gradient boost and regression. Sorry, stochastic gradient descent. I added this line of code to it, just to add in another model, because the more models, if you use all of the models and average them all together, it's only going to do better. You know, it may not get that much better, but the more you add in, the better. So then when we average these all up, I added this line of code in as well, right here, SGD. So before, this wasn't here. This is the average models. Averaging models equals all of these. So you add in whatever models you want to add in. Initially, the code had ENet, GBoost, KRR, Lasso. I just added in stochastic gradient descent. That's all I did. And if you remember, averaging models did better, and here it is here. It does 0.1090. All of these scored 0.11, 0.11, 0.11, 0.11. But when you average them together, you get a slight increase, and that slight increase in accuracy matters. Now we do the meta model, where you can learn how exactly this works if you want to, but mainly it's just taking the best from each model, stacking it, and it's better than just blindly averaging the models together. So same thing here. Here's the code that's doing all of that, and I added SGD here. So that's all I did. The base models are right here. The meta model is Lasso. Print them up, get a score of 0.108. If I play with those parameters more, I can improve the ENet, the GBoost, the KRR, the SGD, optimize each one of those for this data set, and then stack them without actually knowing what this does completely. So that's the benefit of learning how to navigate these things. And here is finally ensembling it, and this is where we get the best score, 0.08. And it does that by kind of using, I think, 25% of each, or yeah, 70% the stacked train, 15% goes with the XGB, and 15% goes with the LGB. He writes it all out, and it's explained pretty well. So if I want to submit that, I'll do that right now just to submit another one and see if it does any better. Submit. Version 2 is fine. Submit. So now it's running. And when this code is done running, I'll have another submission on this competition. You only get scored for one, so if it does better, it'll count it as the better one. If it does worse, it should do like the exact same. I don't think I changed anything just now. But that's it. That's how we submit our results to these Kaggle competitions and kind of enter the competition. So now you could literally go to some of these competitions and see what's going on. You can leave that page too, and it'll still be submitting. And you can enter some of these competitions and get some results. They'll have some code to work off of. It's not like you have to write the whole thing yourself. But these are more complicated, of course. Maybe this one doesn't look too bad. Product recommendation, data. You know, it's going to have a customer data set. Yeah, this shouldn't be too bad. You could use the code that we just used on this, most likely. And that's one way to do it. What else was I gonna say? I think that's it. I think that's it for this video. We learned how to submit on Kaggle competitions. We learned how to implement new linear models from SciKit, and that's all there is to that. So next time we're going to take the code that we took from the housing competition dataset, which is right here, and we'll take that code and apply it to a different dataset. So that will make it a little more complicated. So we're still not writing our own code. We're just taking this code where we optimized it a little bit. We're going to put it on another dataset and see how easy it is to implement this code on, I think I'm going to do the StarCraft player ranking dataset, but I might even do that H&M one, so maybe I'll do both. But that's it for this video. I'll see you in the next video. Thank you for watching. Bye.